This is Calculus with Allenson, problem 2b from the 2003 BC test. What we got here is for A, asks us to find the area of R essentially with respect to x. So we have two functions here, and since with respect to x we need to solve for y. Solving this one for y gets us y equals plus or minus the square root of 1 minus x minus 1 squared. Now on this one, what we're talking about here is when this part of it over here, okay, actually from here to here is what we're worried about, and that's when it's positive, when y is positive, so we don't have to worry about that. On this one, y equals 2 minus x squared, you square root, plus or minus as well. Again, y is positive, so we leave it with just a positive one. Now, for A, to find the area, what we're going to do is we're going to find the area under this curve from 0 to 1. So we're splitting it right at that point. 1, 1 is where they cross. The integral from 0 to 1 of this curve, which is this equation right here, plus from 1 to this spot right here. Now, where is that spot? This is a circle, radius r squared, so the square root of 2 is the radius, so that's where that hits. So from 1 to root 2 of the square root of 2 minus x squared dx. Now for B asks you to set up an expression involving one or more integrals with respect to y that represents the area of R. So instead of going this way and doing rectangles, we're going to be doing rectangles this way. So we're going to be doing this big circle minus the little circle. First of all, though, we need to solve these for x. Solving for this one for x is a little trickier. Let's go. You're going to go x equals, it's going to be a 1 minus y squared, square root it. We're going to get plus or minus. Now the x values here are positive, so we're going to have basically this whole thing is getting shifted over here. Oh, it's on this curve, so we're going to be doing the negative ones. You start at 1, if we add that 1 over here, and we're going to subtract the value, so we're going to be dealing with this part of the curve, which would be the minus. On this one, it's x equals the 2 minus y squared, and then square root it, and this part of the curve from here to here, x values are positive, and so it's the positive one. So here's our two equations, and to find the area we're going to integrate from 0 to 1, the curve on top, which is the x squared plus y squared equals 2, or this one, minus this curve here, minus the bottom one. And so there's a couple ways we can write that. I'm just going to put 1 minus. It looks a little bit better. dy. C says that the polar equations of these circles are r equals root 2 and r equals 2 cosine theta. Write an expression that involves the integrals to find, with respect to theta, the area of R again. So what we want to do is we want to go like that, and since that goes through 1, 1, that's at 45 degrees or pi over 4. So we're going to find the area under this circle, which is this one. from 0 to pi over 4, 1/2 radius squared d theta, plus from pi over 4 to pi over 2, 1/2 r squared d theta. Points on this one. 3 points for each part. For A, we have 1 point for the limits of integration, and 1 for the integrand of the smaller circle, and 1 for the integrand of the larger circle. You can also get a point if you did the geometric area for the smaller circle on A. For B, 1 point for the limits of integration, and 2 points for the integrand. Here are these two parts with the minus. C, 3 points, 1 for the limits of integration, okay, 1 for the integrand of the smaller circle, 1 for the larger circle. Get those backwards.